Okay, so we essentially have been dealing with the same thing for the last, for the last 3 lectures, and we will essentially continue on the same vein in this lecture also. But now, what I would like to do is to formalize some of the notations that we have been using. Now, you see that we have, when we are dealing with voltages and currents, we are talking about an operating point condition, we are talking about an incremental condition. There are 2 types of, essentially what we are saying is, there are 2 types of signals 2 types of voltages we are interested in, right? One that doesn't change with time, or doesn't change, and one that changes, right? So as it turns out, while expressing it in terms of notations, there are some ground rules that the engineering community has agreed upon, and they are as follows. So if I express something like this, capital V, capital A, this means quiescent. I'm referring to a node VA. I'm referring to a voltage VA, where V is capital V, capital A, subscript capital means I'm referring to quiescent quantities. If I say small v, small a, then I'm referring to incremental quantities, or rather incremental voltage in this case, right? So this is equivalent to delta V. What we have been calling delta V, small v, small a is essentially delta V. Then there is one more thing, that is the total voltage, right? The total voltage we get by adding up the quiescent with the incremental. And that notation is V, small v, caps A. So this is total. So when we say, let's for example, sinusoidal quantities, right? So we essentially are referring to delta V because it's changing, it's incremental. So going forward, you will see that very often we will interchangeably use delta V and small v. Okay. Also, this is something that the circuit design community has agreed upon, but I myself have been guilty of abuse of notation many times. So I won't really impose it upon you to follow this strictly, but as long as you understand what is meant, it's okay. For example, if you want to write the total voltage as VA total, I am okay with that. Okay. So what I'm trying to get at here is that as long as you are clear in your mind and you are able to convey what you want, no marks will be deducted. But if you are referring to a total voltage and writing about incremental voltage, that obviously is something fundamental. So there will be penalty for that. So the other but often I see students even in 3rd year or 4th year make mistakes. That is, when they are doing incremental analysis or small signal analysis, they don't desensitize the quiescent sources. What do I mean by desensitizing the quiescent sources? As we discussed, when you have a constant voltage source in the incremental domain, it shorts. If you have a constant current source in the incremental domain, it opens. So in the incremental domain, you should not be seeing any constant voltage or current sources. So they have to be de-energized. That is the direct outcome of the fact that each element is getting replaced by their incremental resistance, right? They are del F, del I del V, 1 over del I del V, right? So which essentially means that in the incremental model, there is no room for that is not changing. By the incremental model means we are referring to quantities that are changing with time or changing per se, even if it's not changing with time, maybe I have incremented it and kept it like that. So essentially ensure that whenever you are referring to, whenever you are sketching your incremental model or a small signal model, ensure that there is no constant voltage or current sources. Okay. So for sake of completion, let me also talk about another set of notations. So let's say I have, I mean, when we sketch circuits, obviously you'll see wires crisscrossing each other. So there are again multiple ways of referring to them. For example, let's say I have a wire going from here to here. So this is node A, B, C, D. Then I can have a situation where I refer to the same thing as this, or I have a situation where I can refer to something like this. So as it turns out, I mean, this is pretty clear that there is an intersection between the two nets, A and B and C, the two lines, because I have expressed it with a junction dot, right? And this is also pretty clear. These two are not intersecting because I have put this semicircle. Now the confusion comes with this, whether this is intersecting or this is not intersecting. So as it turns out, if you follow the convention that whenever there is a non-intersecting line, I will use this notation, then this becomes non-intersecting. This becomes intersecting, sorry. I mean, this is essentially what I'm saying is, if you use these two in conjunction, then this is non-intersecting and this is intersecting. And if you use these two in conjunction, then this becomes non-intersecting. And this one becomes intersecting. So what I will do throughout the course is I will use this. One of the reasons I like this, because if you have multiple loops, multiple intersections, then this semicircle kind of becomes messy. So I will use this junction dot topology to demarcate if it's intersecting or not intersecting. Okay. Let's move on. So you must have noticed in ESC 201 also, and the way I have been dealing with diode circuits in this course also, that, I mean, with the example that I simply took throughout. This is VA or VD. I said that you can assume this voltage to be, let's say, 0.65 volts. Right? Why do you think I say that? Is it a fair enough assumption, or just to make my life easy, I have done that? Any comments? I mean, any answer to that? Okay, that's
we simplify the diode model.
Yeah, so the question essentially is that I have been saying, I mean, whenever I have been doing these diode analysis, right? Whenever I've been doing this analysis, I started off, even in the question paper, I started off and say that for finding quiescent point, assume this to be 0.65 volt, regardless of the current. Right? I mean, if it's on, assume diode to be 0.65 volt forward bias. So why, I mean, is this sacrosanct for 0.65, or it is something we do just to make life easy? There was one comment that we are assuming a diode model of its, right. So we are essentially saying, while finding this, we are essentially assuming that our diode behaves something like this, where this is 0.65, right? So that is okay when you are essentially making a piecewise approximation for diode. But what it is okay for this purposes also. But why is this okay? Can you tell me?
So by practical, we take average.
Okay.
By because
Okay, you said something like, in practice we take average. What do you mean by in practice we take average?
if we take a diode and experiment with different conditions,
Right.
then we take average of all the values
Okay.
that could be that satisfy different experiments. Then their average we can take as the
Okay, so you're saying that if we take multiple values and take average of the voltage drop, it might come out to be around 0.65. Okay. And you said something like it's an exponential. So right. Right. So what he is essentially pointing out is that if I plot my diode characteristics and I know that this is exponential, so this will look like this. So maybe I can say that it's, simply because dealing with exponentials in transcendental form is difficult. So I'll just say it's a kind of sharp rise at 0.65. But the point that I'm trying to get at here is that there is nothing sacrosanct about this 0.65 thing. So why point? It's exponential throughout, right? Why am I setting that? That threshold point at 0.65?
because after 0.65, when there are huge rises in current, only small changes in voltages are observed.
True, but it's true for everywhere, right? I mean, it's fully exponential.
Before 0.65, there is we can see the changes in voltage.
So that's because I have sketched it in this manner. So essentially, if you plot an exponential e power x, how does e power x, characteristics of e power x differ if I am seeing here or if I'm seeing here? All its differentials are also same. Right? So that answer to that lies in some practical scenarios. The practical scenarios, what I mean is, if I am, so let me give you an example. So let's say I did an experiment and I found out that for 1 milliamp current, my so this is my equation. I have a diode where I notice that I have pushed in 1 milliamp current, and I'm trying to figure out VD. And let's assume that VD is 650 millivolt, right? Whatever it might be. So let's assume this VD equal to 650 millivolt. So now I did another experiment where I doubled this current. I pushed in now 2 milliamps. How much change will VD we will observe? This is easy to find because I simply replace these two and then replace the value of IS from the first, right? So how much will be delta VD, right? So in this case, again, I will have IS e power, if this is VD1, if VD2 by VT. So in this case, your VD1 is ln of 1 milliamp by VT, ln of 1 milliamp by IS. And in this case, VD2, VT. I simply subtract and I will get delta VD, or in this case, I can replace it as small VD, will be equal to VT ln of 2. Which is, this is 26 millivolt and ln of 2 is approximately 0.7. So this is 18 millivolt. So as you see that even if I double the current, the increase in my diode voltage is only 18 millivolts, right? I might double from 4 milliamps to 8 milliamps. Then also my change of voltage will be 18 millivolts, right? So essentially what I'm getting at here is that, and even doubling current is not a very common thing. You normally in a circuit, in any, you generally don't see double variations of current, right? You see maybe factor of 1.5 or something like that. So in practical scenarios, what essentially happens is that when you have a diode, then you can essentially say that, fine, I mean, I program instead of approximating my diode as the exact, in this case, for example, if I start off my analysis by assuming the diode voltage to be 650 millivolt, but rigorous analysis needs it to be, let's say, 668 millivolts. How much wrong will I be? Not much, right? So that is why we say that, okay, fine. So for this range of practical currents, right, you cannot say that I will go from 1 milliamp to 100 milliamp and still assume the cutting voltage to be 650 millivolts. Then instead of ln 2, you will have ln 10. Ln 10 you cannot really neglect, I mean, under certain circumstances. So in the milliamps range, which you normally do, even in the labs, when you will do your experiments, you will see that you normally handle milliamps ranges of current. So in those cases, you can approximate the diode characteristics and say that, okay, when it's on 650 millivolts. Maybe if I have to iterate, I will iterate the second go, but at a starting assumption, I can assume it to be 650 millivolts. Now, again, let's say you are designing a very low power design where you have a diode and it's still forward bias, but your diode is now giving you forward bias currents of microamps. In that case, clearly you will not be able to assume that your diode voltage is 650 millivolts, right? Because again, if you plug in those values in your exponentials, you will see that it will be quite different from 650 millivolts. So depending upon the ranges of current that you are using, this whatever diode voltage you are assuming to start off can change. That is, you have to keep at the back of your head, right? Again, for this particular course, we will not go into those ranges of currents. So there is certain assumption that goes in every engineering discipline. So in this particular course, we'll assume that it's 650 millivolts, right? But you will have to keep it at the back of your mind that going forward, if you take up circuit design as a career, don't make this mistake that always assume diode to be 650 millivolts. Or rather, even the 650 millivolts number is also particular to certain types of diodes. Depending upon its construction, how it has been constructed, even for the same ranges of current, you can have different diodes with different voltages, which these voltages are generally called cutting voltages, right? Okay, so there is another way. I mean, now that we know small signal models, I would like to caveat this with, I mean, now you should be able to appreciate why this 18 millivolt change is not significant. Again, let me take you back to this same circuit. 1K, let's assume this is 1.65 volts. So let's assume again this is 0.65 volts. So this current naturally is 1 milliamp. Now if I change this from 1.65 to 1.75, the input voltage, right? So now I change it to, is the same example we took a couple of classes back. So what will be the change in across this diode? What will be the new VDT? Or if I say this is VD1, what will be delta VD or small VD, that is VD2 minus VD1? How will you find?
Delta VA.
Delta VA, yes.
Into RD by RD plus.
Right. So essentially, you will go into the incremental mode, and the incremental mode is what? I mean, the circuit on the right minus the circuit on the left, essentially, right? From the quiescent perspective. So essentially, your increment is 100 millivolt. You have 1K, and you replace the diode with a resistor, and the value of the resistor is 1 over del I del V at current of 1 milliamps, right? So this essentially is VT by ID, where ID equal to 1 milliamp, which is 26 ohms. So this, whatever you are observing here is delta VD. or according to the notation, small v subscript small d. So if this is the case, then obviously your VD is 100 millivolt times 26 by 1026, which I did the calculation yesterday. It comes out to be about 2.5 volts, 2.5 millivolts, sorry. Okay, so as you see that if the incremental voltage change is 2.5 millivolt, what is VD2 now? If I know VD1 is 0.65, what will be VD2 after I have incremented the input by 100 millivolts? VD1 plus VD2, which will be 0.6525 volts. So clearly this is, I mean, if this is my starting point, let's say you have another circuit where you have, I mean, you don't know what was the condition at 0.65 volts. What you didn't know what was the condition here, but this is your starting circuit. How much error will you make? Not much, because essentially, if you see that even if by increasing it by 100 millivolt, you are cutting, I mean, you have changed one part of the circuit by 100 millivolt. You increase the voltage at one part of the circuit by 100 millivolt, but across the diode, it has only increased by 2.5 millivolt. So it's fair enough approximation. And say that I'll start off everything with 650 millivolts, right? So again, there was one question again in the 2 or 3 classes back, is that, see, we are essentially making approximation, right? When we are essentially neglecting the higher order terms, we are incurring some error. Sure, we are incurring error. So how much is that error? And I mean, is it just for mathematical convenience, or there is some logic behind it, right? So at that time, I said that the logic essentially is the fact that you have to ensure that this change, this delta is such that I can neglect the higher order terms, right? So now we can actually establish whether that neglect, I mean, whether that can be, whether that is indeed true or not with this simple example, with the example that we are looking at right now. And what I would like to show you is that, so again, if I go back to the same diode models, or rather diode circuits. So in this, in the circuit on the left, which I am calling at the quiescent circuit or quiescent network, I know that this current ID1 is 1.65 minus VD1 by 1K. That is equal to IS e power VD1 by VT, which is equal to 1 milliamps, right? Because we assume that this to be 0.65 volt. So but in the circuit on the right, I'll have to find out ID2. ID2 is 1.75 minus VD2 by 1K, which is equal to IS e power VD2 by VT. Now, if I assume that VD2 equal to VD1 plus small, it's a delta VD, right? So now I say that this delta VD has all the terms, linear, non-linear, doesn't matter. Then till now I have not made any approximation. what I'm trying to get at here is that the motive of this part of the lecture is to try and convince you that even if I neglect the higher order terms, I'll be fine. But for that, I have to assume that this delta VD contains the higher order terms. So let's assume this delta VD contains the absolute change, right? The total change, not only the linear change. So in this case, I'll just replace VD2 with VD1 plus delta VD. So what I'll get delta VD by 1K is equal to, so I know that IS is 1 milliamps times e power minus VD1 by VD2, VD1 by VT. So I'll replace that. So I will get, no, sorry, I made a mistake here. Right? VD1 is 1.65 volts. Sorry, VD1 is 0.65 volts, right? So if I replace here, so you get 1.65 minus 1.75 minus 1.65 plus VD by 1K, 0.65, thank you, will be equal to IS e power 0.65 plus delta VD by VT. Okay, so here it was 0.65 because VD1 was 0.65. So I replace the value of IS from equation 1 in equation 2. So what do I get? I get delta 1.1 minus delta VD by 1K becomes 1 milli e power delta VD by VT. Right? Okay, this one. Right? So
either we can remove the delta or write the small.
So I reckon the small, either way, doesn't matter. So we get this 1.19 minus delta VD is equal to e power delta VD by VT. Right? So now, what do you think? Can you comment on the order of delta VD here? And now note that this VT is 26 millivolts. So delta VD will be lesser than 26 millivolts or more than 26 millivolts. If I do even numerical approximations, it has to be lesser. As it turns out, it's much lesser, right? Because this is almost close to 1, right? So which means this has to be, the exponent has to be very close to 0, right? So which essentially points to the fact that you are okay, even if you neglect the higher order terms, not delta VD per se. If you are looking for the linear change in delta VD, you cannot change, you cannot neglect the delta VD. What I'm getting here is that a small signal model also gives you a similar answer. In fact, in this case, I think if you do the calculation, I don't have the numbers as of now, but this delta VD comes out to be around 2.49 volts. So in this case, we got 2.5. But if you do the full calculation, you will probably get 2.49 or 2.48, something of that order. So what I'm trying to get here is that you are okay even if you neglect the higher order terms. And if you are okay, neglecting higher order terms, then why carry forward the mathematical burden of dealing with those so many terms? I can as well jump them and go to a linear model, right? Okay, fine. So before I move on, right? So essentially, the first module of small signal analysis, incremental analysis is done. Before I move on, any questions?
You would approach that is e power x equal to 1 plus x.
Yeah, you can do that, right?
And then
Yeah. Or you can simply do numerical, right? I mean, you don't have to do hand calculation, just plug in the numbers and then. This is the original method. If you assume e power x to be 1 plus x, yeah, then there is no difference. But you can actually take two, three terms there and then do. Then see what is the effect of the second one. I mean, x squared term, x cubed term. We can put them together. Yeah, not in that, because they have been neglected the higher terms right at the beginning, right? Okay, fine. So, any questions? Any conceptual questions? Conceptual lacuna that you want me to address? Okay, fine. Yes. Right. Okay, so his question is, when we did this small signal analysis, we said simply that we are finding out the quiescent. This is V1, this is I1, and finding out the tangent here. And we are replacing the increment here of delta V1 with, we are essentially saying this delta I1 is equal to the slope M times delta V1, right? There is no plus additional term here, right? Do you agree? So if there is no plus additional term here, then this by definition is linear, isn't it? So that's what I meant. So this line, the equation of this straight line will be some y equal to mx plus c, or in the sense that in terms of absolute I1 V1, this will be some I1 equal to some m V1 plus some c, or some V0, some I0. This is not a linear form, but I am not particularly bothered with the entire straight line. I am bothered with delta I, delta V. So which essentially means that if I do a del I, del I1, del V1, I end up with this, which is perfectly linear. That's what I meant. Exactly. So in this case, M is conductance, but yeah, so 1 over M is resistance, right? Okay, fine. So let's move on. So at the beginning of the class, if I take you back to the even to the introductory class, I talked about the fact that amplifiers are workhorses for analog circuits, right? So we have to come up with ways of designing amplifiers. Then I made an ad hoc statement that you need nonlinearities to make amplification. I didn't expand on that. I just made a statement. So what I would like to do is take the next 20 minutes or so to expand on that, right? So when we say amplification, essentially what we, in this context, in this course, what we essentially mean, or trying to mean is, let's say I have a network N, and I have an input, which is say Vp sine omega t. We are not trying to amplify any DC input, not in this course. Let's assume we have a time varying input, Vp sine omega t, and you have a load RL, right? Or rather, let me approach it in a different way. So let's say you have a load RL and you have a source Vp sine omega t. I want to amplify Vp sine omega t and apply it across RL. So essentially what I'm looking for is if I observe my voltage across RL, I should be getting some A times Vp sine omega t. This is what I am expecting, where A is more than 1. Right? This is my expectation. So essentially what I'm trying to get at here is that I want a network N. I want a network N which can do this job for me. Right? So what characteristics do I need in this network to absolutely have, right? What is the necessary condition for this network to have this condition of A greater than 1? So note that if I am asking for, if I am saying that I want an amplification of voltage and I'm observing the voltage across a resistor, inherently I am saying I want an amplification of power, right? Because power is voltage squared by R, right? So essentially what we are looking for is we are looking for a way to get a power gain. Okay. So what I'm looking for is, can we get power gain? How can we get power gain? So what I mean is that power gain is if you have an input current I1 and if you have an output current I2, input voltage in this case is Vp sin omega t, and your output voltage is V naught. So what I'm essentially looking for is there a way I can get the power that I'm looking in, the power that power of the net circuit that whatever power is going in and whatever power I am observing at the output, there is a difference, and not only that, I should have higher power at the output. That's what essentially I'm looking for. So let's assume that this network N is passive to start off. There is no active source, there is no voltage supply current source inside. It's completely passive. So, and let's assume to start off, this is LTI. So can I get power gain out of this? Yeah, so passive means it cannot generate its own power. So whatever comes out has to be at least less, can at max be equal, not higher. And if you have some dissipative element inside N, it will be lower because the stuff inside the box will consume power, right? Power is conserved, so output power cannot be more than the input power if there is no other source. So that means that we need a power source, right? So let's assume that we have another port. We could find a port inside this network N where we could stick in a battery. So now this network is still LTI. Now can we get power gain? Yes. We can get power gain because we have a VDD as source, right? So if this is so let me do this analysis quickly. So we have to assume some things, obviously, because we don't know what the network N is. So since we have said that this is an LTI, I can use superposition, right? So if I use superposition, what can I say? I'll just desensitize one of the sources once and find out the output and do the other one with the other source the next step. So if I desensitize VDD and find out what is the output voltage, I will get V naught to be equal to some alpha times Vp sin omega t plus some beta times VDD. Right? This is using superposition. What can you comment on the factors alpha and beta with respect to whether it's more than 1 or less than 1?
Alpha should be greater than 1. Alpha should be greater.
But can it be? Let me try to convince you from the power perspective, right? So what is the output power? What is the average output power? V naught squared by R, which is equal to. So let me get rid of R for the timing. I'll include use R at the end. So what will this be? This will be alpha squared Vp squared sin square omega t plus squared plus 2 alpha beta Vp VD sin omega t. Fine. So let me do the easy ones first. What do you think the average of this term is? Same. What do you think the average of this term is? 0. And what is the average of this term?
Alpha square VT square by 2.
Alpha squared VT squared by 2, because sine squared omega t can be broken up into 1 minus cosine of 2 omega t, and average of that cosine of 2 will go to 0. We'll end up with alpha squared VT squared by 2. So my average power, my output power, the out average is divided by R divided by R. So surely this power, this total power can be more than the input power, because I have this term of VDD, right? I can have VDD to be whatever. If I'm not satisfied, I can keep on cranking up the VDD. As long as beta is not 0, I can get. But note that here I would like to bring to your attention is that, can you comment? Can you relate these equations? Can you relate this equation and this equation and tell me what is the frequency component, or rather at what frequency would you see this power and what frequency would you see this power? Okay, let's do the easy one first. At what frequency would you see this power at? 0, right? That is coming from the DC, right? This is essentially this one. But at what frequency am I expecting an amplification?
2 omega.
No, right? Why 2 omega?
Because
okay, forget about this equation. When I'm expecting an amplifier, if I put in VP sine omega t, what am I expecting at the output?
I mean, amplified
fraction of the same stuff, right? So this is now, I'm curious here. I want to know, why do you say this comes from 2 omega?
Because 1 plus
expansion of this leads to 2 omega, but that 2 omega terms gets averaged out, right? So, okay, so let me expand this. So your alpha squared VP squared sine squared omega t squared VP squared by 2 minus cosine omega t. Now you're doing average. So this average of this goes off, right? So you're ending up with alpha squared VP squared by 2. So my point is, this alpha squared VP squared by 2 is the power of which signal? What frequency signal?
omega.
Omega, right? It's basically, I can take you back to class 11 physics. I don't know when you learn this nowadays, but if you have a input frequency, if sinusoid of 1 volt sine omega t, what is the power? 1 squared by 2r, right? It is the power associated with that sinusoid. The act of finding the power, in the act of finding the power, average power, I am multiplying it with itself, right? It's I times V, because I is also at the same frequency. So I times V becomes essentially V times V by R. So that's why you are getting V squared by R, right? This act doesn't change the frequency component of the signal. The act of finding out the power is not changing the frequency component. But the important thing to note here is that this power that we got is the power carried by the sinusoid at omega, not 2 omega, at omega. So now can you tell me, this power, will it be more than the power that has gone in? Am I able to get power amplification using this system at omega, not the total power? I'm not talking about the total power at DC and AC. No, right? Because again, it's equivalent to saying that when I can get the same expression if I desensitize this, if I short VDD to ground and find out what is the power across RL, right? So then essentially an LTI system allowed me to use superposition, and that's what I could get, right? So essentially, even though the total observed power can be as high as you want by cranking VDD higher and higher, you won't get that power at the frequency that you are looking for. Make sense? So essentially, even if you have a battery, even if you have n number of batteries, an LTI system cannot give you power amplification at the desired frequency. Okay. What is meant by you will get a power at a frequency? Good question. So what am I looking for? My input is a sinusoid, and my output is in the example that I showed, your output will have a DC, right? Your output will have, take this example, your output has a DC and a sinusoid, right? So essentially in time domain, it will look like a DC. It will look like a sinusoid riding on top of a DC, right? So now if I look at the
signal, you only the signal on the
no, you will get the total. This is the total, right? So this
graph, V versus T.
This is T. This is T. V versus T. Correct. So if I have you used spectrum analyzer ever? No. Okay. So what I am trying to get at here is that if you do a Fourier transform of this, or if you do a Fourier analysis of this, you have done a Fourier analysis, right? So you will get frequency components. What frequency components you will get? You will get frequency F will be at 0 and omega naught. Now I'm trying to figure out how much power is there in these frequency components. Each signal is carrying a power, right? What is the power carried by a particular signal? Now, if I say that the signal at omega naught is carrying so much of power, it's equivalent to saying that that frequency has so much of power. That's all I know.
What is the issue?
Why? Okay, so that's what. How can alpha be greater than 1? So let me take you back to the first example. Can alpha be greater than 1? When there's a reason I'm going into the power domain. Alpha being greater than 1 means what? You are getting a power amplification with this network itself. I didn't understand. Yes. Okay, so you are saying adding more, you are adding more energy to the system, but not at the frequency that you want. Let me ask you, let me then expand on this again. So again, network N. How did we get that alpha times term? So we had to desensitize the VDD, right? And when you desensitize the VDD, if this is VP sine omega t, this is V naught, we said that V naught is equal to, so output power will be equal to V naught squared by R, where V naught was alpha times VP sine squared omega, alpha squared VP squared sine squared omega t by R. Right? Why am I able to completely chop off? Because it is LTI. Yes. So this is, you cannot use, superposition is not valid in nonlinear system. Superposition is valid in LTI. That is why I can chop off VDD, which means it is equivalent to saying I can treat each source as if no other source exists. I can do my analysis by de-energizing other sources. This is the sole reason why you are not being able to transfer power from one source that is operating at one frequency, or rather, if a source is operating at a certain frequency, you cannot transfer the power from that frequency to another frequency because all the operations are linear. In order to transfer power from one frequency to another, you need nonlinear operations, right? If you have an input at omega naught and you want a signal at 2 omega naught, then you need a square term in your network. Without that squaring operation, you cannot get 2 omega naught.
powers to be like a sine wave just bigger.
Exactly.
But that is not happening.
Exactly, right? So for example, I am using a PA system and I am speaking, right? PA system is a battery, but my voice at whatever 1 kilohertz or 500 hertz is getting amplified. Not necessarily, you are not hearing the battery.
Adding that DC is not really what we want.
Exactly.
That is way more difficult.
Right. I adding the DC. There is no. I mean, if I only give you a static, right, that doesn't have any information, right? It's the change that has the information. So I want to take the power. I want to take the power from the battery, but I don't want it to supply at DC. I want to take the power and supply it at some AC, some whatever frequency I want it to be supplied at. Right.
We want to amplify the DC term which is coming from the omega naught wave.
I want to amplify my signal at omega naught, but I have to take that energy from somewhere. So I am taking the energy from the supply. But if I simply take the energy from the supply and put it in an LTI network, that energy in the supply will be at the frequency of the supply. And the frequency of the supply is 0, so my purpose is not served. So that is the sole reason. Because you need frequency translation, you require a nonlinear element in the network. Okay, so that is the sole reason you want it. Okay, make sense? Okay, fine. We'll meet on Monday.